my name is Layla Dawn. I'm a PhD student at the University of Texas at Austin. I'm super excited to talk to you today, even though it's digitally and not in person, but thank you for tuning in, I guess I'll say. So I am working on creating a machine learning program to automatically identify cave entrances in Belize, Guatemala, and Mexico. So this is a chapter of my dissertation, and I'm going to talk to you a little bit more about that today. So I started this project about 3 years ago, two years ago, and I got interested in this project because I was actually in Guatemala at the archaeological site of El Zotes, because I do all of my work out of archaeological field camps. And I was working with an archaeologist to find potential caves on this very large, heavily forested tropical site. So what we were doing was we were looking at some really high resolution LiDAR that we had from an airborne survey with about 1 meter spatial resolution. And we were looking for areas of the LiDAR that had really, really steep ravines and canyons. And then we were pulling up the point cloud, which you can see here, and looking for low areas like this little tiny dot inside of this red box. So that, indicated that one of the pulses, the laser pulses, from the LiDAR sensor on the airplane had penetrated the canopy, penetrated this, solid ground surface, and indicated that there might be something below the ground surface, some kind of, void that point had reflected off of. So that's what we were doing. And then we were hiking all day, 8 hours, 10 hours to get to these sites. And macheteing our way there, and most of the time we weren't finding anything, though if you can believe it, we actually did find like 3 caves in this manner, and it actually was a pretty exciting summer because we also happened to have a National Geographic crew out at the field site, working with the archaeologists when we were doing this, and they thought what we were doing sounded cool, so they actually came out with us on a day that we found a fairly substantial cave with a lot of Maya pottery in it. So we had an archaeologist out and we mapped all of that, explored the cave, and ended up in 15 minutes of a National Geographic documentary, which was definitely a fun experience. So as we were doing this, it was lots of fun, but like I said, not super efficient. So it occurred to me, I have some GIS skills and some coding skills and an undergrad degree in geology. So I wonder if a computer could help to identify locations that are more likely to have caves. So ever since then, 3 years ago it was, I've been working on this project and some other machine learning things that I won't talk about today. So right now what I've done is created a beta version of a computer script that's capable of predicting likely cave entrances. Last summer, so 2019, I had planned to ground truth the predictions that my model made in Guatemala, but instead, with about 3 days notice, I learned that our permit had fallen through and we were no longer able to go to Guatemala. But I had colleagues working in northern Belize who said, you're welcome to come here, we've got a spot for you. And luckily, because this is an actual computer program, I was able to get their LiDAR, right away and run it through my model. And then I went to northern Belize, which was unplanned, and ground truthed my model and actually came up with some exciting things that are what I'm about to talk to you about. And then based on these ground truthing results, I'm building up my model and changing it, making it more accurate, integrating some other features now. And programs, in general, programs that teach computers to automatically identify landscape features are really useful both inside and outside of academia. So, things like natural hazard monitoring, like sinkhole and landslide potential, forest inventory, natural resource management and conservation, like mapping archaeological features, which I also work with, are important uses. And then, urban development like sidewalk or telephone pole planning. There are lots of applications, and machine learning is really growing, although there has not been anything done with cave mapping thus far, other than what I'm working on. So landscape modeling, just to give you a little bit of background, landscape modeling, such as what I'm doing, has a very long history. And in the past few years, machine learning and LiDAR, as well as some other types of remotely sensed imagery, have become really growing parts of this field. So there's been some work done with manual cave entrance identification using LiDAR imagery, But more work has actually been done with machine learning identification of sinkholes. There are 2 or 3 papers about that. And then, like I said, I'm also applying some of this to identify archaeological features that are located in those same areas where I'm looking for caves. Because again, I work with all archaeologists, so they think it's great that I want to learn about caves on their site, but they also would like to learn more about archaeological features that they may not know about because they're so hard to get to and obscured by vegetation. So there are like a small handful of papers doing this that have been published in the last 2 or 3 years. So I'm drawing from methods in all of these fields for landscape modeling and machine learning. All right, so just a brief overview of the program here. I create a series of raster layers for cave and not cave points using my training data set, which you can see here. This is LiDAR imagery and about 39 known caves that exist, believe it or not, in Suwannee, Tennessee, not in Central America. This is where I went to college, and I use this data set mostly because it's a data set that I was able to get to train my model on. So the karst here is, similar to that of Central America, but of course it would be better to get more training data from Central America if possible. But, more training data is always better from anywhere. It creates a model that's capable of recognizing more types of different features. So then I added in, a bunch of not cave points, and then I trained my model, picked the most accurate model, and then I ran the train model on unclassified data from Guatemala and Belize, which is what I ground truthed last summer, and now I'm improving the model. So just a little more detail about the model itself that I just provided an overview of. So here's this LiDAR data set from Suwannee, Tennessee. I began by drawing a buffer around each of those dimensionless cave points so that that buffer would kind of capture like any of the morphology associated with the cave. And then I created a polygon where I cut those buffered cave points out, which enabled me to generate several hundred random not cave points that represent the background landscape. And then from there, I extracted the geomorphometry for cave and not cave points. So what I mean by that is that I created a series of raster layers for these points that captured within that buffered area their maximum slope value, their land surface roughness, the curvature of the slope, and the elevation. And then in white are other things that I'm currently adding in to make the model more refined. Then with that data, I pulled all of that out of GIS and I brought it into Python, programming language. And I created a matrix for my training data set. So you can see here all of those morphometry values that I just showed. And then that is cave tag is 1 for a cave and 0 for a not cave. So I encoded it in that way. I split my data into training and test data sets so that I had something to train on, and then like data that the model hadn't seen yet to test on, and scaled it all between 0 and 1 to make the values normalized. I trained with a type of model, a type of classifier called random forest that uses a series of decision trees correcting for overfitting to classify my data. I tried a couple of other types of models like logistic regression, but random forest did work best. You can see my accuracy and cross-validation scores here. And then I fit my model to all of the training data so that it could learn better, and I ran it on unclassified data. And I used I generated predictions for that unclassified data. So you can see here, these are UTM coordinates of predicted cave entrance locations in northern Belize. And this is a visualization. So this is basically the map that I worked off of last summer. The darker purple areas are areas that have a denser number of caves predicted. So those are the areas we were interested in ground truthing. But you'll see it's not perfect. I do have work to do on the model. You can see this really dark circle over here in this floodplain. That's not a cave. There's a big slope difference here between the stream and the surrounding floodplain. We did not ground truth that because that was absolutely impossible to get to through very, very dense wetland vegetation. So there is, some geologic knowledge is required here of what makes sense and where you'd expect to find this stuff. So ground verifying last summer was lots of fun. You see me here figuring out how to work my GPS. I was actually able to get that map that I just showed you with the purple circles on it onto my GPS, as well as the DEM without those circles, and toggle between them. And that really made for super efficient field work because I could get us to all of these sites in the most efficient way possible without going over every single hill. We found a number of things, lots of small voids like you see in some of these pictures, lots of big rock shelters, and then on a day that I had extra machete help, I decided to go to a really far point that my model had identified, super far from the road, no trails or anything. So we're hiking for 4 hours. The guys that are helping me out and macheting are not happy with me because it's hot, it's sweaty. I seem to have managed to have chosen somewhere that couldn't be accessed without going all uphill. And then we go into a clearing. We come out into a clearing, and this is what's in front of us. So Mike, the technical caver that I brought along with me for this sort of thing, rappelled into this thing here. There's a whip scorpion. This is a 200-foot long, 100-foot wide, 115-foot deep sinkhole. It has sheer limestone cliffs on all the sides that are quite soft in some areas, as you can see. This sinkhole is actually 2 adjoining sinkholes that are like in the shape of an 8, and they're connected by a land bridge that you can see here. I think it's actually a collapsed cave complex where the land bridge is part of the roof that hasn't collapsed. And then you can see this feature all the way at the bottom underneath that land bridge that's kind of dark. That could be an entrance to a part of the cave system that hasn't collapsed. Mike did go down and he approached it and was 10 feet away, and he looked into it but wasn't really able to get a good look because the bottom of the sinkhole was extremely steep and extremely loose, and we just decided it was too dangerous and that we couldn't safely do it. So he came back up. But this was incredibly exciting. We had 3 local guys with us, one of whom was in his 70s, and all of them said they'd never seen or heard of anything like that in this part of Belize, and there's nothing published on anything like this in northern Belize. So this was a really exciting find for us, or at least we thought so. And then we did find some other caves that were much smaller. You can see Mike's feet here sticking out of one, and I'm standing in front of one here with Norvel, who's the world's best field assistant. So just to wrap up, we did find some caves with the program. We also found some cave-like features like small voids and rock shelters. In addition to this method being much faster than manual cave entrance identification, it also has successfully identified features that aren't necessarily visible in the LiDAR. So the smaller cave is shown in this upper figure here that says cave, and you can see the cave is not at all visible. And then the larger cave, of course, in this lower picture that says sinkhole, is extremely visible, but only if you know where to look for it and you've zoomed in. It's really not visible when you're looking at the entire LiDAR zoomed out. And then this picture with the red box inside of it is one more picture of that sinkhole with Mike looking very small inside of that red box at the bottom. It's just really hard to capture something like this on a camera. And I also didn't have the world's best camera because I didn't expect to find anything like this. We're lucky that we even had rope. And then just to wrap things up, here are my final maps, a couple of final maps. So these show both the areas where there were predicted densities, high densities of caves, and then overlaid on top of them are the features that we actually found during ground truthing. So caves, voids, which, just small openings in the rock shelters, possible choltuns, those Maya man-made caves, tunnels, and then a couple nothings. So now that I have ground truth the first season, I need to improve my program. So that involves first improving prediction accuracy by integrating other raster layers, especially point cloud low points, statistical and spatial analyses to look for patterns in areas with caves, more training data that's really important, either that I generate myself through fieldwork or that I get from another site or another person, And then the overall end goal is a geographically transferable script that works across Central America, where the user doesn't need to know Python and can specify some parameters, click, and generate predictions. And of course, with some tweaking, this methodology should work in other parts of the world as well. And this is an end of season picture with my amazing field team from last summer. So thank you very much for listening. I really appreciate it. I would love to hear from you if you have questions or suggestions or thoughts about my methodology or the project. I'd love to chat, so my email address is here. And if you'd like to do a call, you can email me and we can go ahead and set up a call. Thanks again, and have a great day. Bye-bye.